Any questions?
Slightly older daughter is reading the earlier parts of. I was reading like how if we see a curve in the germs picture, like when you do a function field and we look at germs and all, then what does poles even signify for that? Like in the germs picture.
No, there you don't see the poles, right? Because a function is not defined at the pole.
Then like what does that even mean? Like basically when we look at cases like all rational maps to K1, like fine line.
Well, what it means is this DVR represents non-negative valuation. I mean, when you are looking at a point, the germs is basically this, it gives you the DVR.
DVR are basically like just exactly like irreducible minimal polynomial in a way.
No, polynomial is just one element. I'm saying the set of all functions, that's the DVR. So that represents around the point. In the germs, this is non-negative valuation. 0 represents unique maximal ideal. Sorry, positive represents unique maximal ideal. 0 represents outside the maximal ideal, the germs. And then the negative, which you are asking about pole, when is the point pole? Those are the functions that are outside the DVR. So it's big K minus DVR. Those are the functions which actually are undefined at the germ, and they have valuations that are negative in all possible integers.
I can't understand the geometric picture.
There is no geometric picture.
About these poles.
So because those functions are not defined at the point, so they are in the complement of germs. So the
what is the exact motivation to study the L shape?
Oh, that is not clear. Yeah, that I said in the very beginning, that why Riemann came up with his Riemann theorem, that is not clear to me. I think it was natural for them in that century because genus was already defined geometrically and they wanted a computational way to compute genus. So for them, they were just looking at an alternate algebraic criterion. And that happens, I mean, they must have tried many things and this thing must have worked.
I was thinking like the open sets are very dense, so can like lot of poles mean that this open set is like smaller in some sense? Because technically they are very dense, but you have very few points that are not defined. The number of points are not defined. Are they connected to the
But this you are talking about the Zariski topology.
Yes, connecting to the Zariski topology. Poles.
No, this is not enough for to make sense of genus or wholes. No, that is too weak. That is simply this algebraic property that closed set, you are looking at the zeros, so zeros are few, non-zeros are far more. So non-zeros basically is the open set and 0 is the closed set.
Can we count like notion of how small is connected to that? The number of non-zeros and zeros, maybe that is connected to genus somehow or localized with.
But that is a concept which is independent of genus. It doesn't know about genus. Genus can be anything. Open sets will always be dense. That's not enough. In fact, anyways, open set is something which is just sitting at the level of geometry. While whatever interesting we are doing, it's actually is happening in the functions. So functions are above the points. So, and the functions are of 3 types, which are in the germ with positive valuation or in the germ but invertible, and the ones which are not even in the germs. So that for that precision you need the valuation negative, 0, positive. But this still is not enough to see why. So this LD sheaf is actually technically it is called a vector bundle. So these are rank 1 vector bundles on a curve. Why the vector bundles are defined this way? I think I gave this motivation via the approximation theorem. So you want to understand what are the functions whose poles only come from this set of points. So that must have been the basic starting point, but it is still, we are not bringing the holes here. So why will such a thing measure holes? That must have been just an accident mainly by Riemann. So it is really coming from one mind. Whose Riemann hypothesis today we will finish. So let's start. Any other question? Okay, so the place where the theorem that we want to prove is in this format. So for a Galois cover of the projective line, and over a finite field of size q, the prime being p, just assume that the size of the field is sufficiently bigger than the genus. This we can always ensure because genus is limited by the degree of the curve, while q is unlimited, so we can take sufficiently with q. Then we will show that these points n1 c sigma, the Frobenius action is the same as his sigma action. Those points are q plus error term, upper bounded by that. So this is not saying anything about lower bound. Lower bound can also be 0. If we show this, then we have seen that Riemann hypothesis is implied. So what is the proof of this? So if n1 c sigma happens to have one point, call that point p on the curve, and then with respect to that define these LD sheaves. So use L of AP, take A to be big enough. So that's one, and second is LB, again B is big enough, and we use two different pullbacks. So we use the phi, which is basically sigma inverse Frobenius, that's LA phi, and we use a different Frobenius, which is the basic absolute Frobenius raised by prime p, mu times, so p raised to mu Frobenius. That's LBP mu is the pullback of this sheaf, which is explicitly just that. It is just F composed with the morphism. F comes from LB. So remember that this F has, if it has a pole, it can only be the point P. It cannot have any other poles. So we are focusing on really this outside the germs at P, the point P. And we have these injections. LA phi functions are basically just they are sitting in L of AQ, and similarly LB P mu is sitting inside L of B P mu. This is simply by the definition of the map. And now what we will do is we will multiply these two sequences. So how do we multiply? We just basically we formalize it by tensor product of vector spaces. So that's the multiplication map. So we are saying that as long as Q is big enough compared to BP mu, this multiplication map, what it does is that it takes a sum of tensor products and maps it to a sum of actual products. So now G1, G2 is just a function, and by the sequence, by the two sequences, you can see that G1, G2 is actually a function in L of BP mu plus AQ. So we are just, so I'm simply calling G1, G2 as G3. In general, it will be, the way this action will extend is you will have a sum of rank 1 tensors. Each rank 1 tensor will be converted to a polynomial by multiplication, and then you sum it up. So you remain in L of BP mu plus AQ. That's an injection. The first arrow may not be an injection because, well, it's a sum of rank 1 tensors. When you multiply, it may be 0. That's very much possible because tensor may not behave well with functional multiplication, ring multiplication. So for that we need the assumption Q is large. So why will it that suffice? So yeah, this is a tricky proof. It's not immediately clear what is the connection of this injection with Q being large. But you will see very soon that this Q being big is important, is critical in fact. So LA has a tower of K spaces. So K is L0, then you have L1, LA minus 1 and LA. And so this actually gives you a decomposition of LA as this sum. So this is, recall what L1 is. L1 is just L of P, the point P, and L2 is, and LA minus 1 is just L of A minus 1 times P and so on. And so they are naturally there is this sequence of subspaces, tower of subspaces. So you can do mod Li vector space modulo a subspace. Now we don't know which ones of these are 0 and which ones of these are non-zero, because sometimes Li minus 1 may be Li. The theorem we had was only about subspace in LD sheaf. We did not have exact result. So we had exact result for adels, right, but not for the LD sheaf. But anyways, their sum will be LA. And we know that the dimension of this is less than equal to degree of the point, which we have 1. So these are really either these are 0 or these are cyclic subspaces, vector spaces, dimension 1. So which means that there exists a K basis F1, F2, Fr, R at most A of LA, such that for all I strictly increasing valuation, right. This is possible because you just look at these 0 or cyclic quotient vector spaces, and the generator which you get, for example, from L1 mod L0 versus L2 mod L1, by the definition of this LD sheaf, you can see that the valuation is actually decreasing. So basically what Li mod Li minus 1 is L of IP mod L of I minus 1 P. So if a function exists here f, then it means that what does it mean? So the function of course can have only poles from the point P, it has no other poles. So whatever you will get from Li plus 1 mod Li and whatever you will get from Li mod Li minus 1, there will be a difference in the valuation. Should I say like that? So now valuation, which way is it? So F2 will have a bigger valuation. Right? Hopefully this should be clear because F2 comes from more possibility of multiplicity of P, it's I plus 1P, while F1 comes only from IP. And notice that LIP is being is the modulus in the second one. So since it is the modulus, what you will get will genuinely have a higher order of P. I mean higher pole. P will be a pole of higher multiplicity. Or then maybe since it's negative, I think it's the opposite way. It's like this. It's minus I versus minus of I plus 1. So yeah, so these are different valuations and you can just arrange them in this way. So let's not use the same f. So we have found this basis and now we write from the hypothesis, this LB tensor LA. So any element G in the product or equivalently from the pre-image, which is the tensor product, any element G can be written like this. It's SI composed with absolute Frobenius P mu times Fi composed with phi. I goes from 1 to R. The SIs come from LB. Right, because something from LB P mu, that's SI composed with absolute Frobenius P mu, and something from LA phi, which is which LA we have fixed a basis using FIs. So just write in that basis FI composed with phi in this order.
R exactly R. SGFI.
Sorry.
SG comes from the first space. FI comes from.
Yeah, but you just LA has a basis F1 to FR, so you just have to look at that, and for each Fi phi, collect everything as Si.
You're doing basically a dot product in that way.
No, it's not a dot. No, it's not really a dot product. It is just simply a product. I am just writing in terms of the basis of second component, which is F1 to Fr. So with F1, whatever, kind of think of it as collecting the coefficient of F1. So the coefficient of Fi is Si. So I am just collecting the coefficients together, that's all. So the question is, when is G 0? Because we want to show injection. So that is violated only when G is equal to 0. So let's check this. So this, the way we have sorted Fi, increasing valuation, what will happen, and the Fi phi actually raises to Q. So the gap of 1 in the multiplicity or in the order of P actually scales up by Q. So what is happening is, in the second component, the valuation with respect to P is growing very fast. It's in step of Q. And so somehow intuitively SIs cannot cancel. So we'll show this by the only order we have, which is order of P. So let's apply, let's first say that SH is the first non-zero SI. And let's apply valuation on G. So let me write down the equation. Equation is minus of SH sigma I goes from H to R So on this, when we apply the valuation, we will get so P raised to mu times the valuation of SH. That's for the first factor at the SH factor. For FH factor, you will get Q times this, and then it's a sum. So valuation on sum is greater than equal to min over I. Plus Q times Fi. Right, this is clear. Left hand side valuation has to be at least valuation of each of the summands, and valuation on product is additive. So we only have this operator available because both SH and FH, only poles we know are this point. So we just apply this. We don't have any other information. This will suffice actually. So now this is greater than equal. So the min of this is at least min of VPSI is, it's all coming from LB. So it's at least minus B. And which implies that P raised to mu VPSH is at least minus P raised to mu B plus Q times and sorry, this was all I. Yeah, and valuation of Fi minus Fh is at least, this difference is at least 1. So you get that this is at least Q minus P raised to mu B, which by the way is positive because we assume Q to be large. So what this is saying is that SH has P as a 0, point P as a 0. But SH, the only possible pole is this point P, and you are saying that this is a 0. So that's not possible. This means that actually SH is 0. Right? It's a rational function, it should have zeros and poles. But if both of them only possibility is point P, then essentially 0, it's a 0 function. And that's a contradiction. So this contradiction implies that G is not 0, which basically means that G was an arbitrary element in this LB times LA, so you get that to be an injection. So this is a really neat trick that we can now actually combine the two sequences by tensor product, and the replacing it by multiplication keeps it, there is no information loss. So let's draw that diagram now.
So the rise, and if S is 0, then means G is 0, right? Like all the S's are 0, right?
No, SH was the first SI not equal to 0.
Oh, it's contradiction.
Yeah, yeah. By definition of SH. So this is the diagram. LB P mu. So this will be the most important diagram of this course because this is what proves the Riemann hypothesis. So there is a map from here to and this is the tensor product version. So this is by claim 1. By claim 1, this is actually an isomorphism. It's injective, but also these were finite dimensional vector spaces, so you actually get an isomorphism, and this is the multiplication happening. Right, so you can think of this as a commutative diagram which takes from LBP mu LA tensor product to LA phi, then it multiplies, which is there is no information loss, and tau maps that thing to LBP mu LA. What is the map? I mean, phi is essentially this Frobenius map. So if you apply the inverse Frobenius, then every element on the LHS has a associated natural image in LBP mu LA. So that's the well-defined linear map. Just applying phi inverse on this component. Yeah, so this, I mean, the multiplication map or equivalently the tau map, this may not be injective. So claim 1 doesn't say that it's injective. Why not? Because see this, it's LA, it is not LA to the phi. So LA to the phi had the advantage of Q being there, which is bigger than BP mu. But in the middle one, this LA, this actually there is no Q present. There is only P raised to BP, BP mu is present, but with A there is no Q. So claim 1 does not apply here. As minus BP mu plus Q raised to 0 is not positive. So claim 1 required minus BP mu plus Q to be positive, but there is no Q, so here actually you only have Q raised to 0. There is no phi present, so you can't run that proof here. So claim 1 only applies on the first vector space, not on the second vector space. So the multiplication is may not be injective, and hence tau may not be injective. And what this will give us is the possibility of a polynomial G such that tau G is 0, and that is what will prove the Riemann hypothesis. So just observe that if we assume BP mu less than Q and we assume that LB LA is greater than L of BP mu plus A, then there exists a non-zero G such that tau G is 0. Okay, yeah, that was fine. Implicitly, G is in the first vector space, and its image is 0, so it's in the kernel of tau. This exists because, I mean, BP mu less than Q gives you the injection by claim 1. LB times LA big means that the middle vector space the first vector space, that it has dimension exactly LB times LA, right? Because it is actually isomorphic to the tensor product, and the tensor product has dimension LB LA. So the domain is big while the range is small. So there has to be an element in the middle which is vanishing under tau. So we use kernel of tau as follows. Okay, we pick this element big G, which is now guaranteed to exist in the kernel, and let us study that. So the representation of G is exactly as before, I1 to R, right in that basis. Such that tau G, what does tau G do? So tau G is, it just removes the phi in the end. And then it vanishes. Okay. So with phi it was not 0, but without phi this is vanishing. So we have found this polynomial. Observe that G is a p raised to muth power. Is this clear? Because the SI part is clearly p raised to muth power, the Fi part is qth power, and Q is at least p raised to mu. So the whole thing is actually a p raised to muth power. So G is a p raised to muth power polynomial with this property, tau of G is vanishing. Now let us, so the interesting thing is that these points that we were interested in, N1 C sigma, so any point big P or Q, any point big Q which is fixed by phi, notice what will happen. When you evaluate G at Q, phi Q will become Q. So you are evaluating tau G at Q, that's 0. So all the points that we want to count are zeros of G. So that is the major property. This was Bombieri's construction. Such that phi Q is Q G evaluated at Q is actually tau G evaluated at Q, which is equal to 0. Right? So the points that we want to count, they are actually roots of this, they are zeros of this polynomial G. Oh, why? Just look at the action evaluation of G on Q. So the SI part on Q and the FI phi part on Q. So FI phi part on Q is what? FIQ. So it's as if phi is absent there, which means that you are actually evaluating tau G. But tau G is identically 0. As a polynomial, it is 0 without any evaluation. So tau G is absolutely 0. That's the magical thing. So we have actually constructed a polynomial G which contains all these roots that we want to count. Now all we have to do is control the degree of G. What is the degree of G? Thus we can count Q's as so first of all p raised to mu times n1 c sigma minus 1, because we have I don't want to take the point P, because the point P this SIFI they actually may become infinity. So I don't want to take P, but for all other Q's G vanishes. So that's n1 minus 1 plus G is a P raised to mu with power. So we have a saving there, right? So it's actually P raised to mu times this, that is less than equal to degree of the 0 part of this principal divisor, right? We cannot directly say degree of G, we have to do it formally. So the formal way is you look at the principal divisor of G, look at how many zeros it has, that's the degree of G0, which you know is equal to, because of rational function, also G infinity, which means the poles of G. But what are the poles of G? Well, poles of G are given by the orange sequence. So poles of G are in multiplicities BP mu plus A. Is that right? That's not right. Let me draw a branch here. Branch is that this is it embeds in BP mu plus AQ, this branch. The G sits there and it is really an element of L BP mu plus AQ. So that's the how many poles it can have, or what's the multiplicity. Which means that we have a count on N1C sigma. That's 1 plus B plus
That is just multiplicity, the degree of point also that come here.
sorry.
Just the multiplicity, right? P mu plus AQ. Degree of the point.
Yeah, the D of a divisor
Multiplicity times the
is
degree of
both the coefficient and the degree of the point. So degree of the point is 1 because we are
I'll be close. Okay.
in K bar, FQ bar, and multiplicity is what you are summing up. So that's LHS. And then the zeros you can switch to now poles. For poles you have information of G because of the embedding in that LD sheaf. So now N1 C sigma is this, correct? But remember that we have A, B and mu all free. We never fix them. So once we fix them, you will recover Riemann hypothesis. So let us just fix and finish. So we can fix A, B, mu by parameter chasing. So let's see, we have to ensure all the constraints. So take mu to be alpha by 2, which basically means that whenever you see p raised to mu, it's actually square root q. Okay, q was p raised to alpha. So p raised to mu is basically square root of q. So what that will give you is a big saving. The square root q is multiplying n1 in this calculation. So there is a saving which is happening in the multiplicity, and a q p minus mu becomes a square root q. So that a part will basically become the main term and b part will become the error term. That's the plan. So for that, let me fix a to be and b to be so these are the conditions that will be simultaneously satisfied. Q is bigger than BP mu, LB, LA is big, and finally this bound B plus 1 plus AQP minus mu, this is smaller than Q plus 1 plus 2G plus 1 square root Q. Okay, so this is the fixing. So we take AB to be just bigger than 2G to allow Riemann-Roch application. Okay, so for Riemann-Roch, this LD sheaf, correspondingly this A and B parameters, they should be bigger than twice the genus. So I've made sure that A and B are just slightly above 2G. B is in fact, well, A is clearly bigger than 2G. B is a bit more complicated because it seems that it is close to square root Q. But remember that square root Q is bigger than G square. So B is also much bigger than 2G. So both A and B are sufficiently large. So we will have control on LB and LA. And P raised to mu is square root Q. Yeah, so there is some intuition in this fixing. And once you fix this, you can just do the calculation, it works. So this is now just simple verification. So what is B So let's first see what B is. B is G plus 1 plus and what is this part? So this part is less than equal to square root q plus G plus 1. Why is that? Yeah, that should be just, let me write in the correct order, then it's clear. Right, the third and the fourth term, when you sum it up, you can see that it cannot exceed square root q, because you get basically G plus 1 by G plus 1. And this overall is less than square root q. Why is that? That is because this G plus 1 minus square root q by G plus 1 is negative. We took q big enough, so because of that it's smaller than square root q. Root q is basically greater than G plus 1 square. Right, so this is negative, so you have less than square root q. Correct. So now B is upper bounded, and which means that BP mu is less than root q times root q, which is q. So that's the first property. BP mu is less than q. So your claim 1 will work fine. Let's now check the existence of G by checking condition 2. So condition 2 is LB LA by Riemann rock. This will be B plus 1 minus G times A plus 1 minus G. So let us check whether this is greater than BP mu plus A plus 1 minus G. Right, that is the BP mu plus A LD sheaf. So all three expressions are given by Riemann rock theorem, because we have made sure that these numbers are bigger than twice the genus. So when is this greater? So that's another sequence of calculations. So when B minus G times A plus 1 minus G is greater than BP mu. Right, that's just subtraction on both sides. If and only if is greater than G So you multiplied by G, brought on the right side and brought BP mu on the left. ठीक, fine. If and only if so what is this? This must be coming from A, I think. A is square root q plus 2g. It's coming from there. And p raised to mu is square root q. So left hand side simplifies, right hand side also simplifies. And which means that you want b to be greater than g times 1 plus root g over q plus 1 or g plus 1. And is that true? B indeed is bigger than that. Right, we took it to B to be 1 more than that. That's also checked. And the last condition now. Which is B plus A square root q plus 1. So what is the upper bound for this? So this is equal to B is g plus 1 plus and A square root q is what? Plus 1. That's what the LHS is. We have to upper bound this. So this is less than equal to plus q plus 1. So essentially the main term that you see here is this q, everything else is error. The main term is q plus 1 and others are just, yeah, they will basically give you this 2g plus 1 times square root q, which we wanted. That's the error term in the Riemann hypothesis. Is that right? Here again this this g plus 1 plus g root q by g plus 1, this is less than square root q. That's what we are using. Yeah, that's all. So this all the conditions are checked, and ultimately we have an upper bound on N1C sigma to be q plus 1 plus 2g plus 1 square root q. So that finishes the proof of the Riemann hypothesis. And then from N1C sigma you can go back to the reductions, and for all curves it's proved. Correct. So you can just state it. For any smooth projective curve C over FQ, genus G, the roots alpha of LT, the L functions satisfy the norm of alpha is square root q, and number of the number of points on the curve and on the projective line, that's q plus 1. This difference is at most 2g root q or minus, between minus 2g root q and plus 2g root q. Because L function has only 2g roots, each has norm square root q, so you get the error as, I mean sigma alpha I is 2g times square root q plus minus. Right, that's the major theorem which took 4 months to prove, and so this implies that if you take q, the main term, I mean you should have to take main term much bigger than the error term for this to be interesting, which means that you take q to be more than g square. Yes. The number of curves is around q plus 1. Okay, so if you go to a field which is sufficiently big, then the main term is almost q plus 1. So you, for a large enough finite field, you start getting as many points on the curve as you have on the projective line.
So I think of it like when you go very large field, every curve almost becomes a line.
Yeah.
Everything.
Yes. Exactly. That is the Riemann hypothesis. And this has innumerable applications. We don't even have time to name them. So one thing which is quite popular is Weyl estimates. So RH has tons of implications. For example, in computer science, we generally use this Weyl estimate. Let's state it. So Weyl estimate for character sum. So let chi be the character which maps finite field elements to plus minus 1. So what this character does is essentially it on alpha, chi alpha is 1 if and only if alpha is a square. So we can write this explicitly also, be the character that maps alpha to the q minus 1 by 2. This is yeah, q is may not be a prime. Even then, do we call it Legendre symbol? I don't know. Yeah, but when q is a prime, so this is exactly Legendre symbol. But in bigger finite fields, this is basically the criterion of when alpha is a square. Inside that field. Of course, it's a square in FQ bar, but in FQ, half are squares, half are non-squares. So that is given by this character. It's a multiplicative function, of course. Okay, so what is the Weyl estimate? So Weyl estimate is interesting in looking at let fx be degree delta polynomial, then the character sum is chi f alpha over all alpha. So what can you say about the character sum over an arbitrary polynomial? So what do you think? And you are summing it up on the essentially on the projective line. On the whole line you are summing it up over the whole field basically. So the thing is f alpha or fx, sometimes it will be a square, sometimes not square, sometimes 0. It's hard to say.
Large enough you will always be a line, so it's exactly half.
Yeah, so it should be something like sigma chi alpha. Now sigma chi alpha is actually 0 because pluses and minuses are equal distributed. So Weyl estimate says that this also is almost equally distributed with the error square root q, constants in delta. Okay, so this is called the Weyl estimate for character sums. Now it's very easy to prove. It's a major thing, we use it in many applications. Wherever finite fields are involved, you will see a Weyl estimate. So all you have to do is consider the curve C for the function field fq x y mod y square minus f. Okay, so the function field is given by this polynomial fx, like this y square minus f. This, by the way, is called a hyperelliptic curve. You will see this in assignments. Uh, so for this transcendence degree 1 field, there is a smooth projective curve, there is a model, and on that you apply a Riemann hypothesis. So why will it help in character sum? Well, because character sum is measuring how many times is this 1 how many times is it minus 1 and how many times is it 0. Well, when it is 0 it won't count. So basically the difference of ones and minus 1 incidents. So let us rewrite it as so what I have done is I have added number of times it's 1 both sides. So then now in the second summand I am looking, the first summand becomes double, second summand I am looking at minus 1, 0 and plus 1. Actually should not say 0. 0 doesn't count. So how many times minus 1 and plus 1? So that's essentially Q except the places where F alpha vanishes, which will be at most Q minus delta. So I can write this as the first one is essentially the number of points on the curve, and the second is Q plus something dependent on delta. Is that correct? The twice of ones is the number of curves, because whenever F alpha is a square, it gives you 2 y's. So that is why it's just counted 2 times. So that's the number of points on the curve, which you know, which minus q you know is square root q. So that's all. Okay, that's, you get this by Riemann hypothesis. That no matter what polynomial you take, I mean, as long as it is not of a very big degree, the residuosity is equidistributed all over the field. So you can do this for other exponential sums. In analytic number theory, there are many other exponential sums available, Gauss sum and variants of that, where you can use both a multiplicative character and an additive character, and you can mix them. So for those you will have to look at the appropriate Riemann hypothesis, and you will get these bounds. So this is a very powerful translation of Riemann hypothesis. Okay, what else? Yes, so the computational questions are open. Given a curve over FQ, how do you compute N1C? In poly log Q time. Okay, so assuming that the finite field is very large, so you can see Q only in binary. If you did brute force, it will take Q time, which is exponential. Can you do faster? So this question is open. We have proved Riemann hypothesis, and we also have this L function, etc., which knows everything, but it's not clear how to compute the L function. The zeta function computation is equivalent to this question. So second is there another interpretation of LT that can help in computation? So is there another interpretation of the zeta function, I mean alternate to what the way we started, which is counting points over all finite fields, because that is the question one. So we can't rely on counting to compute zeta function. We want something else, something more geometric or linear algebraic that we can implement in an algorithm without worrying about counting. So Weil himself actually gave at least one more interpretation on which much of modern math is based. So it is called the cohomological interpretation of the zeta function. So I'll just quickly sketch that, and then we'll finish the course. So cohomological interpretation of LT. So essentially what he observed with some very clever tricks is that this L function, L polynomial, it is the characteristic polynomial of the Frobenius map. Okay, so how did he deduce that? So let's quickly see this. So we have to see the Frobenius, which for us is qth Frobenius, as an isogeny. So what's an isogeny? Well, it's too late to define in this course now, but let's anyway do it. So isogeny is essentially, it will at least be a morphism from curve to itself, but it will be more because now on the Jacobian we have a group structure. So isogeny will also preserve the group structure. So an isogeny alpha, so let me say here isogeny on J, on the Jacobian. So isogeny alpha is a map from the Jacobian to itself which is surjective with finite kernel. So essentially it is an automorphism, but just a bit more relaxed, because it's not saying that it's injective. It is just saying that it's the kernel is finite, because there could have been infinitely many points in the kernel, but no, there are only finitely many. For the Frobenius, actually the kernel is 0. It's only the 0 point which can go to 0. But this doesn't work for other interesting morphisms. So which is why we need to add this finite kernel into it. Otherwise, you will be restricted to only Frobenius, and then you can't build a theory. So let me describe that later. So it's finite kernel, and it respects. It's not just geometric. It respects the group and the variety. Because we want the group to be preserved also. Now we have a abelian group structure. So which is why we have invented a new word. It's not morphism, but it's isogeny. It's morphism in the category of abelian varieties which are abelian groups. So the right term is isogeny here. And since the kernel is finite, we can define that as the degree of the isogeny. So this is basically the size of the kernel. Okay, so isogeny and its associated degree. These are the two things. So example 1 is of course Frobenius. Let me call Frobenius as pi throughout. So Frobenius is an isogeny with degree 0. Sorry, degree 1. The kernel is the 0 point. So it's basically an automorphism of the Jacobian. But there are more interesting isogenies. So take a number and define multiplication by n. Right, because J is a abelian group. So any point D, sum of, basically it's a divisor. Any divisor you can multiply by 2, 3, or even -2, -3, -1, so on. So this is an isogeny. This respects the group structure, of course. And why is this an isogeny? Why is it surjective? It's surjective because any d prime that you want in the image, you can essentially identify 1 by n times d prime in the algebraic closure. So intuitively it is surjective. And why is it finite kernel? Because for that you have to see how many d's are there such that nd is equal to 0. This is another constraint. So on the we will actually see that this also will be only finitely many d's. Anyways, if you restrict the finite field, then J is a finite object. It's a finite group. So you go to a big enough field where all the nd equal to 0 are present. So that also is intuitive that this is an isogeny. N is an isogeny. What is its degree? Yeah, so surjection and finite degree is still intuitive. What is very tricky is calculating the degree. For this, we'll had to work hard. But now, since we have the Riemann hypothesis and all, we can actually reach it pretty fast. So let's do that. Let's do the degree calculation. So for that, I'll need one more thing. For prime L, define this kernel, which is a finite set. It's a finite subgroup of J. So this we call L torsion of J. The L torsion of the Jacobian, and we denote it by JL. So, for example, for 2 L equal to 2 torsion is, they are all these points in J whose order is 2. 2 times that point is 0. This was also a question in the assignment, identifying the 2 torsion. But you don't have to stop at 2. You don't have to stop at L. You can do L square, L cube, and so on. And that kind of gives you J of L infinity. Look at all the powers of L. Look at all these torsion points. That is called TLJ. Or the Tate module. Well, let me not call it Tate module. Let us just continue with L torsion. So the TLJ, basically just the L power torsion part of J, is kind of JL infinity. How do I write it? Kind of this. So TLJ contains all the L power torsion points. And finally, any isogeny alpha from J to J gives an isogeny on the L-adic torsion. simply d to alpha d. Note that since alpha is an isogeny, it respects the group structure. If L times d is 0, then L times alpha d is also 0. So isogeny naturally maps this L torsion or L-adic torsion points to L-adic torsion points. So we will basically work with TLJ and TL alpha. That was originally Wales' idea. And what Wales showed TL alpha for alpha which are kind of combinations of the Frobenius and numbers, right? So you can basically take powers of pi, and you can take powers of pi you can multiply with n. That's again an isogeny, and you can add such things. So you can actually develop polynomials in pi and n. All these are isogenies. Okay, and we'll see what it does on the L-adic torsion. That is how we'll prove some fundamental new properties of the Frobenius map and zeta function. So here is the list. And these are actually not difficult to prove. We'll see the sketch very quickly. So first is that linear map pi on TLJ has characteristic polynomial LT. Okay, so this is the cohomological interpretation I was talking about. That if you see, well, Frobenius is a linear map because on 2 d1 plus d2 pi acts as first plus second. So you can you can ask about its characteristic polynomial. That happens to be the L function. Second is TLJ has a nice structure. So in particular, TLJ is a finite rank ZL module. So ZL is the L-adic numbers. You can think of this as Z model squared, Z model cube. So whatever power you see, that part of TLJ is actually just a direct sum of say Z mod L to the I. And even in the L-adics, it's actually a finite rank ZL module. So this basically follows from the first. The reason is that if characteristic polynomial is LT, which is degree 2g, so from that you learn that Frobenius is acting on a 2g dimensional vector space. So that makes TLJ essentially 2g dimension. And third is for any n, degree of n now gets calculated is the same proof as B, So it comes out to be n to the 2g. And so if you look at the n torsion points, that structure is C mod n to the 2g. Okay, so the n torsion points are again B was for L prime, C is the composite n, but it's the same result. So you can count now how many n torsion points there are. They are exactly n to the 2g, and that group is basically Z mod n 2g many cycles. So these are the structure theorems that Weyl obtained with the cohomological interpretation. So why does A work? Right? What is the idea for that? We actually have all the machinery available. So look at the isogeny pi minus 1. What is the degree of this? So this essentially is n1j. Right? These are all the points that are fixed by qth Frobenius. So fq rational points. So this is jk size of k rational points on J, which is also the same as the degree 0 class group, which we called HC, and which is equal to L1. This we have seen before. And L1 is the product of 1 minus alpha I, so I can actually reverse it also. Right, so degree of pi minus 1 is product of alpha I minus 1, where alpha I are the 2g roots of the L polynomial. This we have seen, this we know. So that's just a recall. And similarly, for all m, what is the degree of pi to the m minus 1? Is the same thing. Instead of fq, you are now going to q to the m. Right? Which should be what? Which now will be alpha I to the m minus 1, because of the base change of L. So if you change the base field, we have seen that all that happens is L function, the L polynomial change, the alpha i's get exponentiated by m. Right? This we had seen in detail. So we have now an understanding of degree of pi raised to m minus 1 for all m. It's just product of alpha I to the m minus 1. So that's all you have to interpret, and then you will get Weyl's theorem. So alpha i's were in complex, but we can also see them as L-adic. So they are in complex, but they are also in now QL bar. You go to L-adics instead of integers. You go to L-adic integers and then take the algebraic closure, so that's QL bar. So we can think of alpha I as being simultaneously a complex number, but also an L-adic complex number. This can be formalized, it's quite straightforward. So the important thing is that now, so let pi act on TLJ with eigenvalues beta I. Okay, so suppose that, so well, pi is definitely on TLJ, it's a linear map. Suppose that its eigenvalues are these beta i's which are unknown. We don't know them currently. But once you make this assumption, what should be the degree of pi to the m minus 1? Right, because we have a formula for pi to the m minus 1 that we have written before in terms of alpha i's. Let's now look at the meaning of degree of pi to the m minus 1 acting on TLJ. So this is equal to TLJ mod do you agree? So the kernel of size of the kernel of pi raised to m minus 1 or any alpha, size of the kernel of alpha is essentially the space, the vector space on which it is acting modulo alpha image of that vector space, the size of that, right? Kernel size is basically equal to co-kernel size. This you can prove just by, I mean, actually this is straightforward by linear algebra. And now what is this? This co-kernel size is the determinant of alpha, where this is acting, I mean the TL version of this. And the determinant is equal to product of eigenvalues. So eigenvalues of these are beta I m minus 1. Is that clear? So basically kernel size is equal to co-kernel size is equal to determinant, which is equal to product of eigenvalues. That's the sequence of purely linear algebraic connections that we are using. So degree of pi to the m minus 1 is nothing but product of eigenvalues, which if pi has eigenvalue beta I, then pi to the m minus 1 has beta I to the m minus 1 eigenvalue. And now you compare the two formulas. This is the beta I formula, and that is the alpha I formula. They are the same, which means alpha i's are the eigenvalues of pi, which means L is the characteristic polynomial of pi. Since this holds for all m, we deduce that alpha i's is equal to beta i's is equal to eigenvalue of TL pi. Which means that pi on TLJ has characteristic polynomial LT over ZL. So if you just look at the l-adic torsion part of J, characteristic polynomial of pi matches that of LT, right? But L-adic is characteristic 0, so it actually matches exactly over integers. So that's it, right? So this is the cohomological interpretation of the Frobenius. If Frobenius on the Jacobian has characteristic polynomial LT. Okay. And it actually implies B and C. B and C are implied by the degree of by degree of L equal to 2G and L torsion respectively. So L to the I torsion respectively N torsion. Basically these L torsion, N torsion, they will be finitely many points. So the group that you are looking at is actually a finite group. What is the size of the group? What is the rank of the group? Those things get, I mean, basically come from the degree of the characteristic polynomial, that's 2G. So this immediately you get. The main thing is part A, that's an amazing result. This is in addition to the Riemann hypothesis. I mean, this is not really using square root Q norm of the alpha i's. So it's an additional result how Frobenius acts on L-adic torsion. But yeah, once we have this, it's a great computational insight. There are algorithms based on this, and still there are open questions. So this has not been used completely. So these results are computationally useful. As one can do model computations. So instead of trying to compute the integral polynomial of LT, you can just say that I want it mod 2 or mod 3 and mod 5. So it's really this insight of Weyl is really made for algorithms. It's a great thing. So the current algorithms time complexity is so there are two kinds of result. One is polynomial in PG and the degree of the curve. and the other is polynomial in delta. Okay, let's see. So log p genus doubly exponential in the genus and delta. Okay, so there are two family of algorithms. I'm not providing the reference because there are many results that lead to this. So first one is used when the characteristic p is small, because then it's a fast algorithm. The second one is used when characteristic is very large but genus is small. So when both G and P are big, it's an open question. Yeah, so that finishes almost everything that is known about algebraic curves.